All right, here we go. This is section 2.3, an object, well, this is actually not 2.3. An object dropped from rest from the top of a tall building falls y equals 3t squared minus 1 feet. In the first t seconds, find the average velocity from 1 seconds to 3 seconds. Probably should say 1 second. So we have the 2 points. So the average velocity is equal to, we just need f of 3 y2 minus y1 over x2 minus x1. It's the slope of the secant line. So it's your old-fashioned slope on this. 9, 27 minus 1, that's 26. Plug 1 in. 3 minus 1 is 2 over 2. 24 feet per second. Sometimes on the AP test, on the free response part, sometimes labels are worth the point, sometimes they're not. 12, not 24, thank you. Yeah. 12.
Does it matter that like some like objects when it's like dropping into negative speed and other ones not?
Oh, this should be negative. Yeah, you're right. You're right. This should be negative. I probably should have put 1 minus 3t squared. Yep. Find the instantaneous velocity at 2 seconds. So this is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. So we have to create this second point by introducing this h, or the second point that's really, really close to 2. That's the calculus. Usually in calculus, the very first step is calculus. Everything after that is something else. Now it's just a lot of algebra. We have the limit as h approaches 0 of 3 times 2 plus h squared minus 1 minus 12, 11? All over h. Limit as h approaches 0 of 3 times 4 plus 4h plus h squared. That's FOIL, and then minus 12 we could put there over h. Limit as h approaches 0 of 12 plus 12h plus 3h squared minus 12 over h. Now we got good news. Anything without an h is going to actually cancel out. The two 12s, they got to go. If they didn't, then we wouldn't be able to factor out an h and cancel with the bottom one. So limit as h approaches 0 of 12 plus 3h. Factor out an h out of everybody. Well, now we're actually plugging 0 in for h, so this is equal to 12 feet per second. So at 2 seconds, it's actually going the average velocity. So that's more coincidence than anything. Don't expect them to be the same. Sometimes they are, most of the time they're not. Any questions on this process? Students be able to recognize various discontinuities. So a lot of discontinuity stuff on the test. In exercise 19 through 24, find each point of discontinuity. Which of the discontinuities are removable, not removable? Give reasons for your answer. So let's plug 2 into x, and we get 3 minus 2 is 1. We have the point 2, 1. Open dot there. Now this is a line, and the slope is negative 1. So we'll just use the fact that the slope is negative 1. Something like this. That's on the left side of 2. On the right side of 2, we'll start with 2. 2 over 2 is 1, plus 1 is 2. And this line has a slope of 1/2, up 1 over 2. Something like that. Find each point of discontinuity. Well, the only potential point of discontinuity is at x equals 2. Everything else is a line. Lines are continuous. That's not a problem. X equals 2 is a point of discontinuity. B, which of the discontinuities are removable? X equals, no, none. This is a jump discontinuity, not removable. How about not removable? X equals 2. Why is this none? Because we have a jump discontinuity at x equals 2. I had a question last period on the homework, and so I'm done with that problem. I'm done with it, but I'm going to use the graph. Let's say the graph looked like this. Open dot here, and then maybe a line there. I'm done with this problem. This has nothing to do with this problem. The question is, what value could I assign at x equals -1 so that it would be continuous to remove the discontinuity? -2. Right there. What value would you give x equals -1 to remove the discontinuity? You'd give it a value of -2, and that would remove the removable discontinuity. Any questions? It's a really simple answer. It's just the y value. So if you still have questions on that question, if you still having problems with it, let me know, and I'll explain it in the homework. I don't think I did a great job of explaining it right here, quite frankly, but it's just -2. How about this one? X plus 2, x plus 3. The discontinuities are in the denominator. We cannot allow the denominator to be 0. So letter A. Find each point of discontinuity. Well, first of all, those cancel. So x equals -2 and x equals -3. Those are both points of discontinuity. B. Which of the discontinuities are removable? X equals -2 is removable. There's a hole in the graph there because the factors canceled out. How about not removable? X equals -3. This is an infinite discontinuity. You can't remove an infinite discontinuity. What value would you assign to an infinite discontinuity? There isn't one. But what value could I assign to a removable? I could assign -2 to that y value, and now it's gone. Find the points of continuity and points of discontinuity of the function. Identify each type. This factors into x plus 2 and x plus 4. So x cannot equal -2, x cannot equal -4, but those cancel. Those cancel. So part A, points of continuity. This function is continuous from -infinity to -4, -4 to -2, -2 to infinity. There's where it's continuous. There is removable at x equals -4 and infinite at x equals -2. On this one, 2x minus 1 has to be greater than or equal to 0. You cannot take the square root of negative values. So we solve. 1. X is greater than or equal to 1/2. So continuous from 1/2 to infinity. Discontinuous, nowhere. It just doesn't exist on the other side. That's not a discontinuity. That just doesn't exist. This one down here, this is almost like a trick question because you can take the third root of anything. So this is continuous from -infinity to infinity. It's continuous everywhere. Don't get tricked. If it has no problems, then there's no problems. Another one could be 3x squared minus 4x plus 2. So this is continuous from -infinity to infinity. There's no problems. There's no denominators and there's no even radicals. So there's no problems with that at all. It's not a trick question. There's just no problems with it. Give a formula for the extended function that is continuous at the indicated point. In other words, how can we get rid of the problem? The problem is if you plug 4 in, square root of 4 is 2, minus 2 is 0. We get 0 in the denominator. We can make, as long as it's minus, we can make anything into the difference of two squares as long as it's minus. We can make this into the square root of x plus 2, square root of x minus 2, over square root of x minus 2. If you FOIL that out, you're going to get x minus 4. That would be x. The outside and the inside would cancel each other out, and the last would be minus 4. So now these cancel out, square root of x plus 2. This graph and this graph will be the exact same, but that one will not have a hole in the graph. We've removed the problem. That's what the question wants. Not a particularly useful problem, but that's what they want you to do. Is any real number exactly 2 more than its cube? Is any real number exactly, is that 2 more than its cube? Is that possible? That's the question. And then give any such values accurate to 3 decimal places. Well, we usually don't solve it like this. We could, but here's how we should solve this one. Let's minus the x over now that we have it set up. Let's talk about the intermediate value theorem. If we have a continuous function, and let's say, forget about this equation for a second. What if we had I'll use numbers and then we'll put variables in here. What if this x value was 2, this x value was 8, and we had the point 2, 1, and we also had the point 8, 5. As long as this is a continuous function, the intermediate value is a guarantee. At the very minimum, there's a line between these 2 points. At the very minimum, there's a perfectly straight curve there. At most, it could curve down below, it could curve up above, but we don't know that. So would you say that there exists some value here that we could plug into whatever this function is that would give us a value of, let's say, 2? Is that a guarantee? Yes, absolutely. It's absolutely guaranteed that there's an x value somewhere in here that would give you a y value of 2. How about, is there an x value in here, let's say it'd be over here somewhere, that would give you an x value of 4? Is that a guarantee? It's absolutely guaranteed. What about 6? Is there an x value in here that would give you 6? Is that guaranteed? Not guaranteed. Could it? It could. This curve could do this and go above, but we don't know that. We don't know outside of it. We only know inside of it. So what does it say? What does the intermediate value theorem say? They call this A, and they call this B. They call this f of A. They call this f of B. So in the middle, they say C. There exists C such that f of A is less than or equal to f of C is less than or equal to f of B. So there exists a C such that f of C exists in between f of A and f of B. So that's how they give variables to it. That's what the intermediate value theorem says, that there is a guarantee of a value in between, as long as the function is continuous. As long as it's continuous. If there's a discontinuity in there, then we're not guaranteed anything. So what does that have to do with this problem right here? Well, first of all, this is a continuous function. So your calculator knows all about this stuff. How come I can't? There we go. Clear, y equals clear x to the third minus x plus 2. Now, if we graph this, we don't really have to, but if we take a look at the graph, yeah, there's a place where this function is equal to 0, because I set it equal to 0. And we can find the 0. We can calculate. Now, when we do the 0, the calculator knows go to the left of the 0. And in this case, that happens to be negative. Go ahead.
I didn't get the theorem. I didn't get the theorem down.
Okay.
And I can't see it.
I'll go back.
All right.
Okay. If I go negative, if I give a negative value, press enter. And then I go to the right of the 0 and say, all right, that value's positive up there. What are you guaranteed? Somewhere in there, there's what? There's got to be a 0, right? Y has to be 0 in there somewhere, because I know it's a continuous function. I gave it a negative on the left. I gave it a positive y on the right. Somewhere in there, it's got to be 0. And then it says guess, and you just back up, enter. But the calculator bases that off of the intermediate value theorem. So then it says give any such accurate to 3 decimal places, negative 1.528 or whatever it was. 1. Know that for the test. If you got any problems with it, let me know. If you don't understand it, let me know. But you got to know that for the test. There's one question on the test about the intermediate value theorem. Continuous function. Find a value for a so that the function is continuous. This is a line. This is a line. So the only place where there could be a discontinuity is at 2. That's the issue that we're looking at. So if I plug 2 in for this, we get 4 plus 3, we get 7. That better equal the same value when I plug 2 into there. That better equal 2a plus 1. So 2a plus 1 better be 7, or else the two lines are not going to meet up at 2. They'll have two different y values. So 2a equals 6, a equals 3. So how can we make this a continuous function? A better be 3, or else it's not continuous. Everybody good? All right, here we go. This is a little practice for the test and just a little bit of review. I thought that this would probably give students a little bit of difficulty. This is right out of the homework. But this is based on the fact that we have the limit as x approaches infinity of sine of x over x is equal to 0. Remember, the graph looks like this up here at 1, and then it's that kind of octopus looking thing like that. So limit as x approaches infinity is 0. Limit as x approaches 1 is of 0 is 1. So I want to get as many of these as I can possibly get out of this. So we have the limit as x approaches infinity of x sine of x over 2x squared plus 2 sine of x over 2x squared. So we use like a reverse common denominator. Instead of putting two things together, we're going to split it back up. Gone with one of those. So now we have the limit as x approaches infinity of, it's really 1/2 times sine of x over x. So I got one of these now. I know that's going to be 0. One down, one to go. These cancel, and I'd really have 1 over x times sine of x over x. So I got another one. I got 2 of them out of there. Well, now I know that each of these is going to be 0. So this becomes 1/2 times 0 plus 1 over x times 0. I know that. But what happens to this piece right here when x becomes really large? What does it go to?
0.
This is also going to 0. So we have 1/2 times 0 plus 0 times 0. The final answer is 0, but you got to somehow get to that. Yeah, go ahead.
Would it still work if you pulled out the sine of x from the numerator? So you did x plus 2 times sine of x over 2x squared, and then just cancel it.
Yeah, that'd work. Times. Yeah, because the ending behavior of this would also be 0. Yep, probably a quicker way. Yeah, I like that. I don't know why I put that one on the right. I don't know. It's like I started typing it. Someone asked me a question. I never got back to it. It's just we'll do it just in case it matters. 1 over 2x. It's 1/8. There's no tricks to that. Just x cancel and you plug it in. So it's like I didn't finish that problem. I'll get back to you on it. Find a simple basic function has a right end behavior and then a left end behavior. Oh, I had this crossed out. I just wanted to do one of these. Not that we couldn't, but I went to clear the board and I copy this and then I take white ink and I just paint over it. That's how I eliminate it. Then when I erase the ink, all of a sudden it appears. So there's a little behind the scenes action. How about the right side? What about infinity squared plus e to the negative infinity? And if you don't like using infinity, just pick a fairly big number. As a matter of fact, even at 100, you'll see a huge difference between these two values. Now you're comparing 100 squared plus 1 over e to 100, which this is very, very close to 0, right? Really big number in the denominator. So for a, y equals x squared is dominating the values. I didn't leave myself a whole lot of room. For b, y equals negative 100 squared plus e to the negative 100, or I think of it as infinity. You can just pick a fairly big number. Now you're comparing really, what is it, 10,000? 10,000 versus e to the 100, so 3 to the 100. You think 3 to 100 is going to be bigger than 10,000 or smaller?
Bigger.
Much bigger. It's going to be huge. So now for this one, it's y is equal to e to the negative x dominates for b. Go ahead.
So when I'm writing these answers, we don't need any sort of limit statement. It's just the y equals.
These are not, I mean, technically it's probably a limit, but no, you don't need a limit statement for this. All right, what's happening to this as x approaches either plus or minus infinity? 2 over plus or minus infinity is the same as 0. So plus 1. For plus or minus infinity, the minus 1 isn't really going to play much of a role in this, so I can eliminate it because we're going to infinity. Then what we're left with is 5x squared over x squared. Those cancel, times 5. 1 times 5 is 5. For both answers. The negative infinity would not matter on this. Find the vertical asymptotes of the graph of f of x. Describe the behavior to the left and the right of each asymptote. So part A, 2x plus 4 equal to 0. 2x is equal to negative 4. X is equal to negative 2. So there's your vertical asymptote. Vertical asymptotes happen where the denominator is equal to 0. But now we have to describe the behavior without a calculator. So here's what we're going to do. What if we had something really close to negative 2, but on the right side? So negative 1.999 squared minus 1. Would that be a positive value or a negative value? What do you guys think? Positive. What about negative 2.001 squared minus 1? That's going to be, what do you think? Also positive. So the numerator around negative 2 will not affect the answer because it's just going to be positive. Let's talk about 2 times negative 1.999 plus 4. What do we think that's going to be, a positive or a negative? Positive, because this will be slightly under 4, right? Slightly under 4. But that's enough so that when you add 4, this becomes positive. How about 2 times negative 2.001 plus 4? So the negative will be slightly more, absolute value, slightly more than 4, so that'll be a negative. So on part B, limit as x approaches -2 from the left equals what? On the left side. Not value, because this is going to infinity. Remember, this is a vertical asymptote. This is to the left, right? That's to the left, so this will be -infinity. Limit as x approaches -2 from the right. This is on the right side, right here. That's right side, and it didn't matter on top. So positive over positive is positive infinity, or just infinity. Any questions on that? All right. Anything down here? Nothing. Connect to a Wi-Fi network. Okay. I don't want to. Oh, that's it. We have section 2.3 today, and the quiz tomorrow is only over section 2.1 and 2.2. So we got 2.3 today. And I'm going to take a grade on this one right here. So you got your first video grade today.